Okay, so let's do this merry-go-round example here. And in this example, we have a merry-go-round, certain mass and radius, it's spinning, and some kid jumps on. So here's our final situation, our initial situation. Okay, so we have this little kid of mass little m, it's kind of hard to see there, who jumps on merry-go-round, and that was our initial situation. So, this problem combines not only energy, well, part B talks about energy, but it also includes considering angular momentum. So some stuff we talked about in the last chapter then is kind of being incorporated into this problem here. And we need angular momentum to solve the first part of the problem. Okay, so the first part of the problem, we're asked to find the final angular velocity of the merry-go-round after the kid jumps on it. So this is a conservation of angular momentum problem. And so the initial moment of inertia times the initial angular velocity is final moment of inertia times final angular velocity. Okay? So we need then to calculate the moments of inertia in either situation. And the moment of inertia of a disk, remember, is 1/2 mr squared. So there's the moment of inertia. That looks very funny on the board right there. 1/2 mr squared is the moment of inertia of a disk. Now, if we have a disk and then a point mass, let's consider our child as being a point mass here. So we have now a disk plus a point mass. So the moment of inertia is the sum of the moment of inertia of the disk plus the moment of inertia of the child. And so the moment of inertia now is the disk, so 1/2 mr squared. Okay, that's for the disk, plus the moment of inertia of the child. And for a point mass at a distance r from the rotation axis, it's just mr squared. So that's little m times the distance from the center of the circle, which is r, so little mr squared. Okay? So there's our final moment of inertia and our initial moment of inertia. Okay? So solving for this expression up here, we want to know what the final angular velocity is. And so that's initial moment of inertia divided by final moment of inertia times initial angular velocity. Okay, so initial moment of inertia is 1/2 big M r squared. Okay, there's our initial moment of inertia. Divided by final moment of inertia, which is this, 1/2 mr squared plus little m r squared. Okay? And that's times our initial angular velocity. Okay? Now, the r squareds all cancel out here. Okay? So there's r squared in each of these terms here, so they all cancel out. We don't need that for this problem. Okay? So we can start plugging numbers in now. The final angular velocity is 1/2 times big M. Big M is 120 kilograms. So we have 1/2 of 120 in the numerator. And then in the denominator we have 1/2 times 120 plus little m. And the mass of our child is 22 kilograms. Okay? So that times our initial angular velocity, which was 0.5 revs per second. And it's fine to leave this in revs per second for now. All that means is that our final answer here is going to be in revs per second as well. Okay? So when you solve that, you find that your final angular velocity is 0.366 revs per second. Okay? So there's our answer to part A. Now in part B, we want to calculate the final kinetic energy compared to the initial kinetic energy. We want the ratio of the final kinetic energy to initial. So we're going to need some space here, so I'm going to go ahead and erase this. Part B then. We just found out that our final angular velocity was 0.366 revs per second. So that's our answer from part A. Now in part B, we want the ratio of final kinetic energy to initial kinetic energy. Now kinetic energy, remember, is 1/2 I moment of inertia times omega squared. So this is 1/2 I final, omega final squared, divided by 1/2 I initial, omega initial squared. Okay? Now the 1/2s cancel. And now we can plug in our final moment of inertia here and our initial moment of inertia. So let's do that. Final moment of inertia is our 1/2 big M r squared. And that was our initial, sorry, our final moment of inertia is 1/2 m r squared plus little m r squared. Okay? Divided by initial moment of inertia, which is this, 1/2 big M r squared. And that's times omega final squared divided by omega initial squared. Okay? Now the r squareds cancel, just like they did in part A. And we can now plug in values here. So 1/2 m is 1/2 times 120 kilograms. Remember, big M is the mass of the merry-go-round. Little m is the mass of the child, so plus 22, divided by 1/2 of big M, which is 1/2 of 120. Okay? Now times omega final squared divided by omega initial squared. Now, again, we don't have to convert these to radians per second here, because we're just as long as they're both in the same units. Okay, so we have revs per second. Just as long as these are both in revolutions per second, we're going to be just fine. Okay, since we're calculating a ratio, just as long as we're consistent with our units, everything's going to be okay. So omega final squared is 0.366 squared, and omega initial was 0.5 squared. Okay? So we do this calculation here. This is all kind of, you have to do this all by itself first. And then do all this calculation. The number you get for the ratio of final kinetic energy to initial kinetic energy is 0.73. Okay? So what that means is our final kinetic energy is about 3/4, about 75%, 73% of our initial kinetic energy. So we've lost kinetic energy in this process of the child jumping on the merry-go-round. And so in part C, we're asked, where did that energy go? Okay, so where did that energy go? Well, imagine there is no railing on this merry-go-round. It's just a flat disc. Okay, so when the kid jumps on the merry-go-round, the only reason he actually sticks to the merry-go-round is friction on the surface. So when he jumps on, there's going to be a little bit of sliding until his feet kind of come in contact with the merry-go-round. So this energy is basically lost as friction. Friction when the child jumps on the merry-go-round, and friction accelerates the child at the same speed of the merry-go-round. So it's basically lost as heat, either in friction between his feet and the merry-go-round, or heat in his muscles when he grabs on to the merry-go-round. That energy is basically released in heat in his muscles when the child has to kind of do work on himself to get onto the merry-go-round.